Okay, let me introduce Cory Krug. Cory is the guy that answers your questions when you submit a bug to oaScript relative to Python or Ruby. And he has been a member of the group for, I believe, about 10 years. He is a super developer. I think he was originally at Oracle, and he's been stolen away by Samsung. But Cory has a live demo building applications with oaScript Python. I'm sure you will enjoy his presentation. Thanks.
Okay, can you see my slide for what it is?
Yes.
Yes. Okay, that's my virtual machine. Okay, so this is actually Jupyter Slides, which is something new I'm trying this time out. So a couple years ago, I went through an exercise. I've made oaScript and PyQt combined applications several times, but I want to go through, take something simple and take it through all the processes of all the possibility I can do with it in terms of making a widget that's actually fully into C++ and also a plugin for the Python. So this is kind of what I'm going to show you today. So let's make an application. And so the first thing is I have a little virtual machine here. The setup is from si2.org. I have open access. I'm using the oaScript Python, and then I'm using the NAND 45 nanometer library. That is a free library provided by them, and that's actually good for interchanging with other sources that aren't an NDA necessarily. From the open source side, I'm using Python 3. This is actually Python 3.6. I'm using Qt5 and PyQt5, which is the Python bindings for Qt. All these were installed via Anaconda, and it made it really simple. In addition to that, this presentation was done with IPython, also known as Jupyter, installed through the Anaconda. So usually the first thing I do on any project is kind of explore and prototype, and I usually use a Python shell. In this case, I'm going to show you my IPython Jupyter notebook. And so this is starting from scratch, just to initialize the shell. I just have to do some basic things to initialize, open the libraries, and request read access on the libraries. And so the lib.def contains that NAND 45 library I mentioned. And so when I request all the libraries available, I get a single swig object of that library. So just to explore what cells are in this library, I often use this. This is a Python construct that gives me a list instead of an iterator, and so I can do random access later. And so I got a list of all the cells. I just randomly picked number 20, and it looks like some sort of flop. And then also I can do the same thing where I can list out all the views available of this flop, and I see, okay, that they use the standard symbols. I'm not sure what their functional view is exactly, but the symbols are the main interest, main thing I'm looking at right now. So there's built-in help functions, so you can use help of anything. It provides doc strings of all the functions. This is the oadesign.open function, and there's a multitude of ways to call this. So I'm going to open that flop symbol design, and then let's see what shapes are in it. And so you have to get the top block. You can request the shapes, and so here's all the shapes that are components of that cell, of that symbol design. And so these are the things that, for viewing a symbol, open access symbol, just start looking at these. And one thing I noticed is I don't see any circles or arcs, which is why I said, okay, an XOR cell, if anything has an arc, an XOR cell probably has it. They have a couple XOR cells, and I open up one of those designs, and then I get the shapes of that XOR cell. And so I can poke through and say, okay, this library may not be that interesting. It looks like it's all rectangles and lines and just a little bit of text. So I kind of know what I'll see once I finally can render these shapes. Just looking at one of the OA recs, we can get a bounding box of that. This will be important to take these points into open access or into Qt to draw these. I do the same thing for an OA line, and I get 2 pairs of points. And so, I'm just starting to kind of break down the data and see what's in the symbol and start figuring out how I'm going to start drawing this with my symbol viewer. And so I can get text. This one randomly appears to be pen name. The eval text, which is the last one on the list, is specifically just getting the text, and then you can get more information. So another thing you can do is a dir of any objects in Python, and so that lets me go in and see all the various things I could call off that object. And so I'm going to try the get evaluator name and just find out a little bit more about this, and based on that name and based on what I remember, this appears to be set up for a Virtuoso, because that's their evaluator name. So now I'm going to start looking at PyQt5 and looking at how the painter works in PyQt5. And so PyQt5, even though it's done by different means, that they have all the available functions to call on that. And so I can see how to draw an arc, what they request for that, how to draw everything else. Some of this is going to their documentation on the actual website for Qt and seeing what it is. And so, yeah, I just start looking at, okay, from one of the shapes I can get the, this is actually a text shape. So text, you get the origin. And then also, I was curious how much space these are taking up, because I'll show you later why this is relevant. But this is just, how I kind of explored the object. And like I said, I find Python very useful for this, because anytime open up a Python shell and just try, either get the documentation that's available from the doc strings, or try a few things manually and assemble your program and then kind of move that into your script. So after I explore and prototype it, so I start building the app in PyQt5. And so here's the whole app, and I'll launch it in just a minute. I decided to make this whole thing a symbol viewer Q widget. So Q widget is the most trivial widget. It doesn't really have anything built in terms of how to draw. And so the critical thing is I created a paint event, which is a specific Qt binding to draw any widget that's on the thing. When it receives a signal, this is what it does. The other critical part is for OA, I just have to have some way to tell it what design it should be rendering. So this is a little bit complicated, but basically there's a lot of initial setup, finding the ways to map the two coordinate systems, finding the way to map angles and things like that, and scales and translates and stuff like that. But initially, I get that. Later on, I get down to setting up the pins, and then I just have to iterate over all the shapes from OA and see if it's a rectangle type, see if it's a line type, arc type, which we don't have any cases of that, and ellipse type. I did not render a text type in this case because I still don't know how to scale the fonts appropriately. That's a little bit of extra work to do. And then after I go through all the shapes, then I have to go through all the terminals and draw the terminals. So I choose a red pen, I get the terminals, and then you have to iterate terminals, pins, figs, and for anything that's a rectangle, I would go ahead and render that. And so I'll bring that up. So this is that code. That's probably about 120, 150 lines of code. And then I can select the library and then select the cell that I'm looking at. And I can see, all the cells are basic rectangular shapes. And then ultimately, if we get down to something that doesn't have anything, then I just draw an X if it does not have a symbol, a type, a view of the cell. And so this is a case where this is kind of completed, but this is a very small application. I can bring it up, I can start looking at cells, and then I can find something I don't like it's not centering the object correctly, it's inverting something, it's not drawing it right. I just work on the Python, and then I open this up again, and it's just kind of an iteration at this point, just to say, here's a very simple test bed, here's me looking at symbols, and does everything look correct as I expect it to? And you can use another application that draws symbols to kind of confirm what you have. This library only have one library set, but you could actually select multiple libraries through this. And yeah, this is the rest of it. It's just kind of basic Qt stuff. You build your buttons and your text boxes, and just kind of work through that. And then you lay out the different things, and then just a couple basic props to load the cell names when you change libraries, and to show the symbol. And then this is just basically pretty much boilerplate. You just basically build the dialogue and execute it. So that was the first phase, and this is kind of the point where you could stop a lot of applications if you're happy with the performance. Let me go back to my slides. So, one question is why go further? You can do this. Honestly, everything I've released to my own groups has just been pure in oaScript and PyQt5. I have played with some places where the performance starts bogging down, and I find good workarounds for that. This performance is pretty good. It's low effort. It's portable. This is a script. As long as someone has that installed, they don't have to have any other special things compiled or installed. But this kind of where you start bogging down is of course in the paint methods and stuff like that. When you actually have a specific paint method, and you're going from Python to C++ to Python and back and forth. And that's one thing to consider. So if I do truly have an ellipse, here's how we draw it is we get a bounding box for the ellipse. We do some calculations for the angle, and then we have to do all these different calls to get all these different things. And it ends up, if you look at this, it's 8 calls to the oaScript swig wrappers to create 8 Python objects, and based on the sizes over there, it's probably about 200 bytes for these 8 different objects. So some are smaller than others. PyQt5 is built with a SIP wrapper. It's specific. It's like Swig, but it's specific to PyQt5 to support all these special signals and slots that they use. And so that, whenever you call a function on that, and it's the same as Swig, whenever you call a Swig function, it has to look at every overloaded function, compare all the variables you sent it after it kind of decodes what they are, and then choose which function to call, and then unwrap all the variables. And so if you look at this, you have 8 calls to Swig, you have to do a very, an overload search, you have to unwrap the objects you just wrapped, and then you have to destroy all the Python objects in addition to the memory you have. And so this is kind of one reason why, if you start looking at performance, this is one area where you can improve things if you choose to wrap things more in C++. And so that's the next thing I do is I converted this very basic Q widget to C++. And so there's kind of 3 levels of classes you need. Of course, C++, you're using headers. Here's the 2 same functions that I had on that Q widget in Python. And this is really just everything. And then, sorry. the constructor, and then the two functions are here. And of course, keep a link that symbol. C++, it starts, the open, the loads, the paint events. This kind of looks a lot like the paint event that we had in Python. It's just the usual basic conversion. You have to declare functions. You have to declare variables and a few extra things. But you can really kind of side by side just kind of start converting things over, because most of the function calls are the same. The trick is, you're not Python objects anymore, so everything is direct integers and floats and stuff like that. So it will be faster. So that's that widget part that I had. If we go in to use Qt, you have to use kind of their make functions, and so this is their sort of a make file. I have to create. This is me creating a plugin. So I'm calling, these are my headers. I have to create actually another level of headers that are plugins, and then just a couple resources files, and you just provide the libraries to link in, and then all these link commands, which can are very exactly like make files. From this, we would go ahead and do a make. So I mean, these are all the after this is done. These are all that I really have to do is run a qmake, and that makes the make file, and then make release and make release install. Well, what I'll show you just now is I can bring up Qt Designer, which is this is how you kind of can create some forms, and with that widget and the other files, other couple plugin files I created, my Qt symbol viewer is now available, and I can actually add it to real Qt real Qt projects here. And so this, when you can create a Qt plugin, you can fully install it into Qt, and then it's fully available. And then the next phase is, okay, if I want to use this in Python, how do I get it back to Python? The other files it's actually 7 files total to do this project. So the first 2 are the 2 that I showed you, the symbol viewer widget itself, the header, and the CPP file. In addition to that, you need to have a small plugin file, which is just a little wrapper code around it. It tells Qt what this is, its name, and a few things like that. Beyond that, to use it in Designer, you have to add in another widget, another plugin file that's the plugin for Qt Designer itself, which is what we saw in the Designer things, and then the make file that I showed you after that. And so, yeah, so that's basically now I have a fully usable C++ plugin for this project. And so the next step is, if I want to use this back in Qt5 again, then I have to wrap it in with SIP, which is the counterpart to PyQt5. And so there's a function that it's all Python code now, and it's essentially just another makefile generator. You have to write another little file, which I used sources online, the SIP documentation off of River Branch Computing that makes that where you install that from, and then there's this is actually the Python code that does the SIP wrapping, and so this is calling all the SIP functions. I got most of this online. I found a nice example written for PyQt4, and then I went through and updated it a little bit. So the key thing to notice here is right now, go find a good boilerplate and then you can add the, you have to tell it your zip file to use, which is essentially like a header for all this. And then you have all the includes you need to do, just like you did includes on your other make files. You have to add extra include directories, extra libraries, and then all of these turn into -L commands in the make file. And then ultimately at the end, it's a makefile.generate. And so this is entirely just a makefile generator. And so all this is over in this directory. So here's that file. So when we call this, it generates the makefile. And then from here, we make it and install it. So one thing I should mention is you have to install the plugin on the C++, you have to be writable to a plugins directory that's your Qt installation was built with. To write this, you have to be able to write into your Python 3 site packages directory. And so sometimes you have to have your own version of Python and Qt installed in order to do a project like this, but then that also makes it stable and portable, so nothing has a dependency. And so now that's installed, I can actually call up another, go into my application, and so this is side by side the Python and the C++ versions of this plugin. And this is also a good way, once you get the Python working and you rewrite it into C++, keep them side by side, you'll start to notice if it's drawing incorrectly, if it's not translating something correctly. And you know, this is you know, a good way to validate that your C++ works against your original Python prototype. Okay, so my resources. A SIP has resources on SourceForge. So SIP is the wrapper for PyQt5 that works specifically with how Qt style of signals and slots. This was the next thing is a blog entry I found, which is very useful to me to write all this. That was mostly that most of these files I kind of started with that and then kind of updated them for both PyQt5 and my own stuff. And of course, point out the documentation for the SI2 oaScript working group. You can go to oaScript.org. It'll redirect you to the current place of the site. That's all I have. Are there any questions?
Just one quick question, or rather note. So as of this year, Qt supports Python. So they have essentially their own Python, which they support. Have you tried that in comparison to PyQt5?
For a long time, there was an open source project because the SIP and PyQt5 are kind of, there's some moderately open source, but more of a commercial license attached to that. For a long time, there was an open source kind of version of that to replace that. I don't know where that went. It never kind of was as good.
PySide, right? So you're referring to PySide?
Yes, PySide is now officially supported by Qt.
Yeah, right.
All right.
Yeah, I tried PySide once, and it wasn't quite ready yet. And honestly, for an internal company use, I don't have to worry about those commercial licensing things, and so that's why I've stayed with PyQt and SIP, because it's something I know. It's something there's more documentation out there of. But yes, but PySide is an alternative, and it may be a better alternative if you are more of an EDA company for supporting this and not having to pay some extra license fees to some of these companies for commercial use.
Thanks.
Yeah, quick question. So when you compared, so when you were looking at the speed at which your application runs, you were mostly observing that there was a lot of slowdown due to the data conversions, the SWIG data conversions.
Yeah, I mean, that's what I expect it to be. In general, so this is really the first time I've actually used a straight Q widget in terms of, this is a widget and you're drawing everything with Python.
Right.
Previously, most of the things I would say you're more likely to use the Canvas system, where when you go in and you add rectangles one at a time, and then those are kind of permanently part of the canvas, and so you don't have all these conversion calls except at the very beginning. I found the Canvas can support probably up to about 100,000 rectangles comfortably with the redraws. After that, it starts to slow down a little bit also.
Right. Whereas over here, you basically take over the paint event and you draw yourself.
Yeah. This is actually the symbol, which is since it's only at most maybe 20 items. A symbol's using the most inefficient way to do it, but it's still a very easy way to do it. So if you wanted to speed it up without going into this, you could probably restructure that as a canvas and then try to add in all the equivalents of those arcs and things into the canvas. I think I looked at that initially, and then I wasn't as happy with putting them in the canvas itself.
Thank you.
Thank you, Cory, for a fantastic demo.